Hey everybody, today you can see the title up on the top of the screen. We're going to be working our way through Translating Problems 2. Hopefully you've worked your way through Translating 1. You have an idea of what we're doing on these translating days. The reason why I've grouped together the problems for today is because they all kind of fall into this one category, if you want to think of it that way. They're all problems where I kind of feel like you just got to know how to get them started. In translating 1, we spent time working our way through problems that, you could totally stumble your way through by just translating some language, by changing English into algebra. These problems are problems that I think are best solved if you have an idea of your starting point. So I'm going to argue to you, you have to know how to get them started. After that, you're good to go on your previous stuff. So what I want to do is I want to walk through a number of problems today that kind of have that beginning part to them. Then your job, jump in and practice as many of these as you can to make sure you are comfortable to set up these problems to be able to solve. Okay? So let's jump into the first problem that you see on the screen. You'll notice we have what we refer to as an age problem. When you give that problem a read, you'll notice we're talking about ages. And specifically, we're talking about ages that occur at different time periods. So we start to talk about in the first sentence, the sum of Dave and Steve's ages is 34 years. That's like a current time. And I'm just going to put a little C there. Our current time period, that's the situation. But then when you look at the next sentence, it says 5 years ago, the sum of blah, 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 blah. You'll notice we're working in a different time period. 5 years ago, that was the past. So I'm just going to put like a little P and circle it. What we've been asked to find, what are the present ages? I'm going to underline that in purple. And the only reason I'm underlining it in purple is because that matches the first sentence, what I've put the C circled in. That's the same time period, current. Okay, there's our problem. Now, what I want to do is I want to walk through one way to solve these. By no means am I saying that this is the only way to solve it, not at all. But I do think that this is the way to be able to solve the problem that requires the least amount of memorization. It gives you the greatest ability to stumble. Okay, how could we start it? Well, the question does ask, what are the current ages, the present ages? So I think what I would do is I would create my let statements in that time period, current, present. Now, since the names are Dave and Steve, I'm going to use D and S just so I can keep them straight. That way I don't have to keep looking back up at my let statements to figure out who I made X, who I made Y, or so on. So for my first let statement, I might say that I'm going to let D represent Dave's age. And to be very clear, because I have two different time periods, I'm going to make sure that I specify now. Current time period. What I think I would do, is I could go through then and say that I'm going to let S represent Steve's age now. And if I choose to do that, I've chosen to use two variables in my let statements. I've committed myself to solving a system. So what I could do, and I'm not saying I would, but what I could do, if I just go through and replace that, is I could then say, well, okay, my first sentence says that Dave plus Steve is 34 in the current time period. And then what I could do is I could adjust for the other time period. Now, I'm going to shrink this down and just slide this over because I'm going to now create two then statements. If we're talking about 5 years ago, then D minus 5 was Dave's age. Right? If Dave is D now, then 5 years ago, he would be D minus 5. I would then have the same thing, then S minus 5 was Steve's age. And I could now use those expressions to represent my second sentence. Now that I'm talking about in the past, it says the sum of twice Dave's age, 2 times Dave's age, and, because it was my sum, 3 times Steve's age was, that's just a past tense of is, there's my equals, 61. That now gives you equation 1. You're probably going to expand your brackets, collect like terms in equation 2, and you could solve your system. Okay, there is a way for us to be able to go through, hopefully straightforward and logical. I want to tackle problem 1 a different way. Just as we talked on the previous day, that going through and dealing with a system simplifies the beginning for you, but is going to make extra work later, I'm going to do the same thing now. I'm going to now get rid of the beginning of that second sentence because I'm going to use my first sentence and not use a second variable. So when we see the sum of Dave and Steve's ages is 34, if D represents Dave's age, then 34 minus D is, and I'm going to actually just get rid of that rep, is Steve's age now. And so what I was able to do was to get that going without putting in that second variable. I don't want to introduce it. Okay, it still doesn't deal with the fact that I now have a 5 years ago, a different time period that I need to deal with. This is one step that I'm going to argue to you. If you struggle with age problems, I would recommend putting in. I would still recommend creating then statements for the other time period. It's going to cost you like 10, 15 seconds, but if we're struggling, this makes your life so much easier. If I want to go back 5 years ago, then D minus 5 was Dave's age. Then 34 minus D, which is Steve's age now, subtract off 5, was Steve's age back then. That writing down those two red statements isn't a bad thing at all. As I said, it costs you 15 seconds or so, but now you have expressions you can work with. So when you go to create your equation by using that other time period, that being the red one, you can now say the sum of twice Dave's age, so there's my 2 times D minus 5, and 3 times now. I could just blindly copy Steve's old age. But I'm going to bet and say that you're going to want to simplify that expression now. That I can go and collect my 34 minus 5. That's going to give me my 29. And I could simplify that expression to 29 minus D. And that's going to clean up my equation a little sooner. Okay, what you will notice, I've now created one equation in blue, and you would be good to solve. So when I'm working through translating age problems, that's going to be my approach to that problem. Since we're only translating today, we're not actually solving. Now I'm going to put down a little star and I can just solve that equation. I notice it's going to be a linear equation because when I do expand, I'm going to have d's. I will be able to collect all of my variables into one variable term. So when I solve, I'm going to look to isolate. There we go. Okay. Hopefully that gives you a bit of a walkthrough dealing with some ages, and you would feel comfortable to try some of those problems on your own. Now what I want to do is I want to kind of jump ship on those ones. I want to jump over to a different type of problem. Let's take a look at problem 2. Okay, I want you to pause the video and give problem 2 a read, and then we'll come back and we'll talk about it. Okay, pause it now. Okay, we're back. Okay, as I mentioned at the very beginning, we're going to face a lot of problems today that just kind of have this I need to know where to start feel to it. And this is one of those problems. Now, how can you identify when you're working with one of these types of problems? Take a look at the third sentence. The third sentence says, a survey indicates that, and that's not the part that identifies it for us. What it is that something's going to change depending on the way something else changes. So it says a survey indicates that attendance will fall by 100 people for every $1 increase. A change in something creates a change in something else. And when we further read the problem and we notice that it's talking about revenue, that's what I want to put in your head. If you see a revenue problem where we're talking about a change in one thing causing a change in other, then there's a way to start off these types of problems. So what I'm going to do is just get rid of all of that underline, and here is our start. The way you want to start these problems is to say that you are going to let your variable, and I'll just be boring and use x, let x represent the number of price changes. And I'm going to allow it to represent the number of price changes. Be very clear, that doesn't say represent the price change. I don't know how many price changes we're going to have. The survey in the problem just says every time we increase the price by $1, 100 fewer people are going to show up. Well, maybe we increase it $2, and that's what's going to create the greatest revenue. Maybe we increase it by $1.50. We don't know yet. So what I want x to be is the number of price changes, and then I'm going to allow my function to solve that for me. Okay, the other reason why I've called it price changes and not what the problem says, which was price increase. It's because I don't actually know which direction I want to change the price. What if dropping the price by $1 creates the greatest revenue? I need to be open to both. So by using a word like change, I keep it generic. And now I'll allow the sign of the integer to dictate whether I'm increasing or decreasing. Okay, we'll see what we're talking about in a second. Okay, you write down the purple and you are good. You've defined your variable, you are good to jump in. However, I think you are making a horrible decision if you choose not to write down 2 then statements. So you're going to see me write them down all the time because I think they make your life so much easier. It's a boneheaded decision not to. Okay, what are those 2 statements? Well, really it comes down to what is revenue? So I want to make sure we're good on the concept of revenue. When we have revenue, revenue talks about the money that comes in. You'll notice I didn't say the term, how much money did you make? Because make implies, maybe that's profit. When we talk about revenue, We do not care about the costs we have. There's no bearing on how much money we paid out. Revenue only talks about the amount of money that comes in. So, if we know what revenue is, then revenue is only made up of two things. If I want to figure out what revenue is, then I need to consider two things. How much am I going to charge when I sell it? That's my price. Then, how many of them am I going to sell? There's my quantity. So for me to consider what is revenue, revenue always is the amount you charge times the amount you sell. Right? If I've got a lemonade stand at the bottom of the driveway, then the amount of money that's going to come in from all of my sales throughout the day is going to depend on how much do I charge per cup and how many cups do I sell. So what I want you to do is to then write down two then statements. As soon as I say that X represents the number of price changes, I could then come up with an expression for the price and the quantity. I know that the price, and I'll start with price, right now is $5. That's my starting price. So 5 is my price. But what the survey tells me is that I'm considering increasing the price by $1. So I'm going to increase the price by $1 every time I change the price. So my expression becomes 5 plus 1x. Right? If I decide to put in two price changes, then that's 5 plus 1 times 2, because it would be the $2 increase. Now, the form of that, I understand, is horrible. We should never write down a coefficient of 1, but I wanted you to see it. So 5 plus x then is the price. I could do the same thing to create a quantity expression. I could then say, well, what's my quantity now? Right now, we are selling 800 tickets. So 800 is my starting quantity. But I notice that every time I increase by $1, I'm going to lose, there's my fall by, 100 people. So my quantity is going to fall, so it's going down 100 people every full price change I make. That expression then is the quantity. And there you go. That gives me all the information I need. It really does, to jump in and be able to solve the problem. Okay, I want to come back to that in a moment. We're going to come back and we're going to talk about something we can use as a bit of a check. But that gives me something to talk about with the problem. The problem asked me, what ticket price results in the greatest revenue? And given what we've already worked through, we should be quite comfortable that if you have to find the greatest of something, that's a way of saying the maximum. And if you have to find the maximum revenue, then you need to create a revenue expression. There's your revenue function we're about to build. You'll notice I get to use the blue expressions. Look over on the right side. How do I calculate revenue? It's price times quantity. What I have in blue is the price times the quantity. And there we go. That's straightforward. Okay, given that today is a translating day, we should be good from there. The problem told us to find the greatest, which means we're looking for a maximum. So we should be good right now to say that we would expand those brackets, collect like terms, put it in standard form, and then to find a max, we're going to use our x equals negative b over 2a to find where that occurs. Okay, couple things. I am not solving this problem for you. Remember, that's a different day. But I do want to highlight something in the problem. And I'm going to do it right here. Take a look at that revenue function, and you'll notice we have negative 100x at the end of the last bracket and positive x at the first. So when we eventually expand those brackets, you're going to get a function that's going to start with negative 100x squared. Like, yeah, there's going to be some other, and then there's going to be a constant at the end, but that's for a different day. I want you to notice that what we're going to create is a parabola that has a negative leading coefficient, which means we're talking about a parabola that opens down. And if it opens down, then it has a max. Okay. How do we make sure that that thing opens down? Well, it's because you have different coefficients on your x. You can see those different signs, so you know when you expand it, you'll get a negative leading term. Okay, why does that happen? Well, I want us to be very conscious of something, and I'm just going to wipe out some stuff here. Look back up at your blue statements. I know I'm on the right track when I see different signs in front of my x. To be honest with you, that should almost always happen. That's something that we would refer to as a normal good. When the price of something goes up, then you tend to sell fewer of them. Your quantity goes down. If you were to drop the price of something, then generally the quantity is going to increase. We will sell more. That's normally what happens, a normal good. There are exceptions to that. Like there are exceptions where we may drop the price so far that now people start to question, okay, well, how good is that good? Like, is that product worthwhile? Oh, that price is so low, it must be cheap. Oh, I don't have any faith in the quality of that good. I'm not buying it. Maybe at some point the price goes up so much that people start to go, oh, wait a second. I think that that good has a high quality, and therefore they would choose to buy it more. Take like diamonds, for instance. If somebody told you that they were going to sell you a diamond for $10, you probably do not believe that that is a real diamond. But if they told you they were going to sell it for $500, maybe now you do. You could choose or could find yourself selling more because you're asking more. Those are all odd cases for us. The green is odd. The gold, that's normal for us. Increase the price, drop the quantity. Decrease the price, increase the quantity. So what you see if you look back up at those blue statements, that should happen most of the time. And I'm going to argue to you, it should happen so often that if you ever find yourself writing down blue statements where those two signs are the same, it should make you question the problem. It doesn't mean you're wrong, not at all. But I think it is worthwhile to then go, wait a second. I'm dealing with one of those quirky cases. If this is the situation, let me take a look back up and make sure that I'm good. Okay, we should be good with that. I'm going to put down just that little reminder again to finish off the problem on a translating day. We would be using x equals negative b over 2a to be able to finish off that problem. Okay, nice. That is a good old revenue question. And as I said, unfortunately, you just kind of got to know how to start those ones off. So we're going to let our variable represent the number of price changes, and then we're off to the races. Okay, that was a big problem for us. It's an important one, though. Okay, let's take a look at another one. Okay, there's problem 3, and I think, given our discussion for today, you should be okay to give that one a shot on your own. Okay, I want you to pause the video, and I want you to try to get down to a function or an equation, and then stop there, and we'll come back and we'll take a peek and see how we match up. Okay, try it on your own. Pause the video now. Okay, we're back. So you take a peek. Our school store has been selling shirts, for $20. At this price, we sell 600. We determine that for every $2 decrease, we will sell 40 more shirts. What's the maximum revenue? And you should be saying to yourself, oh, wait a second, this is one of those revenue questions. Explicitly, it says maximum revenue. And it's one of those problems where we notice a change in price causes a change in quantity. This is one of those problems where I need to let my variable, let x, represent the number of price changes. That price I do not like. That's a little better. Okay. We have that as a starting point, and I'm hoping that you followed my guidance to say, let's create 2 more then statements. Okay, I'm going to go through, and I'll deal with price first. Currently, our price is $20. But we see we're going to talk or examine decreasing the price by $2. So I need to drop the price by $2 for every price change. That is the price. Hopefully we matched up. Okay, if I've caught up with you, I think this is a chance for you to try to come up with the quantity expression on your own. Okay, pause it and try it on your own. Otherwise, we're coming along together. If I want to examine now my quantity, well, right now, we sell 600 shirts. But we know that every time we change the price by $2, decrease the price by $2, we are going to sell 40 more shirts. So we're going to be increasing by 40 for every price change. That then is the quantity. I'm hoping we were able to match up, and you've picked up relatively quickly, hey, how we can recognize what we're dealing with regards to a revenue problem. What was the function now? Well, that one's pretty easy. Revenue equals price times quantity. And you get a little confirmation, hey, this is one of those normal goods. A decrease in the price caused an increase in the quantity. Stuff matches up. You, of course, would expand those brackets. I'm just going to write that down this time. You'd put it in standard form. And then we're talking about using our x equals negative b over 2a to find the maximum. Okay, I'm hoping that that one went fairly well. And that gave us another little, or I guess maybe a first case to check on our own, but another example for us to see in dealing with a revenue problem. Okay, what I want to do now is I want to jump into something a little different. Okay, what you see on the screen. It's a pretty quick problem. I'll read through it together. Stewie has $11.15 in nickels and dimes. There's a total of 140 coins. How many nickels and dimes does he have? So what we end up having in this problem is a quantity versus value problem. And this is one of the ones that I want to walk through with you. I think that this could be a problem that fits really nicely into a system solution. However, I really want to make sure that nobody feels pressured too. So I want to walk through it 2 different ways, but I'm going to go through pretty quickly on this problem. The problem asks, how many nickels and dimes does he have? So for me to answer this problem, I need to be able to give the quantity of nickels and dimes individually. That means that I'm going to let my x or my y or my variable represent quantities. I'm going to do the same thing I did in this problem that we did back with the age problem. I'm not going to use generic x and y. I don't want to keep reading back up. I'm going to use n or d to talk about the type of coin. So I'm going to let, I don't know, maybe n represent the number of nickels. Don't just say let n represent the nickels, because now there's some ambiguity to that. Are you talking about the quantity of nickels, or are you talking about the value of nickels? There's no ambiguity in my statement. I said the number of nickels. Okay, if we want to use a system, then your next statement would have to be a let. We're going to use another variable, so there's your d, and you would let d represent the number of, and I'm just putting in a little quotation just to show that I'm repeating the same thing. I'm going to get rid of that in a second. Okay, now what you could do is do a direct translation. I'm going to start with my quantity sentence because I think that's the one that works easiest given my let statements being in quantities. I could now say that my number of nickels plus my number of dimes has to equal 140 because that's the total number of coins. What you're going to notice now, in my orange sentence, that's talking about the value of those coins. So what I would need to do to build my second equation is I need to put the values on the quantities. If I wrote down n plus d equals 1115, how is that even possible? Remember, my variables represent quantities. How is the quantity of nickels plus the quantity of dimes equal to 11.15? How can I have part of a coin? I can't. So what I need to do is I need to put values. That 1115 is a value. So how much is each nickel worth? Well, each nickel is worth 5 cents. So there's my 0.05. Please make sure that you didn't think to put 0.5. You just made each nickel worth 50 cents. Be very careful. I could do the same thing now with dimes. Each dime is worth 10 cents. And now my orange equation represents a value equation. I'm good. You notice you have two equations that both contain the same variables. You could go through and you could solve the system. Like, not to jump too deep into it, but probably solving that system means, you're going to multiply the first equation by, 0.05 or multiply it by 0.1 and then use elimination. Okay, you would be solving the system. I think that's a pretty straightforward way for us to get into solving that equation. It's actually pretty efficient, even with the system. Okay, what I want to do, though, is I want to walk through again, what if we didn't use a system? I'm not trying to dissuade you from using a system. But if the whole goal is to get to one variable anyway, you may find starting off with one variable and not introducing the second gets you there quicker. So what I'm going to do again is going to focus in on my quantity. If m represents the quantity, then that sentence tells me my total. So 140 minus the quantity of nickels has to be, is the number of dimes. Okay, we know our total. If n is one of them, then our total minus n has to be the other. Now I haven't used the second variable, so I can jump right into that first sentence and I can talk about values. How much is each nickel worth? 5 cents. So there's me putting the value of a nickel on the quantity. I'm going to add to that the amount that each dime is worth. And I know that that total value is 11.15, and you are good to go. You'll notice with that red equation, now you don't have a system. You're probably expanding your brackets and now collecting like terms to solve. Maybe you view that as more efficient. Regardless, we're now solving that thing, and we should be good. Okay, what you will notice, second method through, one equation, we were good. But what highlights and makes this problem a little different, it's the fact that you have quantity information and then you have value information. So we need to figure out how to use the quantity and then use the value to build our equations. Okay, I want to jump in and give you another shot at a problem on your own. Okay, I want you to give problem 5 a read, and then I want you to try it on your own. I think we got an opportunity to see where we're at with some of this translating. Okay, pause the video now. Okay, we're back. So the question says, how would you invest $1,000 in 2 types of deposits? One's going to earn 4%, the other earns 6%. Those would be quoted per year. We have to figure out how to split up that 1,000 so that we will receive twice as much from the 6% investment as what we receive from the 4. So whatever amount of money we make in interest has to be double in the 6% investment than what we would get in the 4. Okay, let's see how we did. You'll notice that this first statement that I'm circling in green, that's my quantity. In total, we had $1,000 to invest. So I'm hoping we started off and just said, I don't know, let X. There's nothing here that really leads like 4, 6, I don't know, F and S, I don't know. Let X represent the amount of money. We could have just said the money. That's just as good. Invested. And I'm going to pick one of them. There's nothing in the problem that dictates which one's more important. So I'm going to say at, I don't know, 4% came first. 4%. X represents the money invested at 4%. Okay. If I know that $1,000 was the total invested, then 1,000 minus X is the money invested at 6%. Okay, I now have my variable defined and I have expressions for both my investments. Nice. Okay, the problem says I'm going to receive twice as much income from the 6% investment as I get from the 4. Okay, I want to walk through this one because I think that there's a real common mistake. And I want to make sure we can nail that out. If I went through to translate that sentence, it says you're going to receive twice as much. So we may tend to go 2 times, very good, twice as much, from the 6% investment as what we get from the 4. So when we start to talk about that twice as much, and I'm just going to write in some language here. From the 6% one, notice that isn't my variable at all. It's just me seeing some language. Is equal to the 4% one. And I'm hoping that you can see that that red equation is incorrect. I'm going to go back to something that you did back in grade 8. And I'm going to draw that nice little scale that you had in grade 8. I don't know, something like that, where we learned that equations, equal signs, represents balancing. Read that second statement. You're going to receive twice as much income from the 6% as you will from the 4. So if I was to ask you, which one are you going to get more money from? I hope we would say the 6. I'm going to circle it in green. So if I put the 6 one, and I'm just going to do like a pile of money here. That 6 is bigger. The 4, I'll circle that one in orange. There's my pile of money. There's my 4% one. Look what my red equation now tells me to do. Since it says the 6 is double the 4, if I do what the red says and now double that, I am making the bigger side even bigger. I'm not balancing those two weights. My equation just got really thrown out of whack. They're not equal at all. That the way that I can go through to actually make those balance would be to either take the one that's worth the most and cut it in half, so divide it by 2, or take the one that is less and double it to bring the 2 into balance. A common mistake when we translate that is we affect the side that's really out of balance, if you want to think about it, the greater or the less, and we go more in that direction. Okay, I hope you're seeing then, with my lovely scale drawing, how that red is not true. So you have 2 options. You could then say, well, then you're going to cut the amount made from 6 in half, or you're going to increase the amount made by 4 by doubling it to make them equal. Okay, let's actually create a good equation then. Well, what I need to do then is I need to talk about the income, so the percentage that I'm going to gain on each. Take a look back at my first let statement. That's X, that's the amount of money. I'm making 4% on that. So I'm going to get 4% on every dollar I invest in that deposit. So there's my 0.04x. Same thing as before, make sure that we don't call it a 0.4. That's 40%. That is one heck of an investment. That 4 needs to be doubled to bring it up to the amount I'm going to make on the 6% one. And that is one possible equation we could use. You'll notice I am doubling the 4% to make it equal to the value, the 6%, on what I invest. Of course, we had another option for that equation. Perhaps you said the amount you make on the 4% investment would be equal to the amount you make on the 6% cut in half. There are your 2 options. Pick one of those and you are good. You'll notice in both of those, you should be good to simply isolate. We could solve that to figure out how much was in each. Nice. Okay, what you've seen in the last 2 problems are examples of quantity versus value. We used our quantity to create our let and then statements. We then used the value to build our equation. So what I want to do now, change gears. Let's tackle another problem. So take a moment, give the problem you see on the screen right now a read. Okay, pause the video now. Okay, we're back. So you've given the problem a read. It says a rectangular sheet of tin has those dimensions. A uniform strip is to be cut off around the sheet. Now, we might have some questions about what that word uniform means. We'll talk about that in a second. If the remaining area is to be that, calculate the width of the strip. Okay, what I want to do is I want to talk about the context of this problem. So I'm going to end up drawing a picture. So it says that it's a rectangular sheet. So if I draw a rectangle, there we go. The sheet is 15 centimeters by 9 centimeters. Now, it says a uniform strip. What that word uniform means, same size. So, a strip that is the same size is to be cut off around the sheet. So what that means is if I was going to cut like this little thin strip off that end, then I would have to cut off that exact same width everywhere. Notice like I did that same thing on those other two sides. If I now went and cut off a strip this wide on that last side, that would no longer be uniform. That the way that I can go through and cut off a uniform width would be the same amount on every side. So something like that. That's what uniform means. Okay, let me shrink that back down. If the remaining area is to be 112 centimeters squared, so when I cut off all of this stuff around the outside of that purple, the rectangle that's left over, which is now the blue one, that has to have an area of 112 centimeters squared. The problem wants me to figure out, well, how wide of a strip do I have to cut off to make that happen? Okay, I'm going to get rid of that diagram a little bit because I do want to like maybe make it a little more functional for the problem. So I'm going to get rid of all that little red stuff that we actually, you know what, let me just get rid of the whole thing and I'll draw a brand new one. So there is my rectangular sheet of tin. It is 9 by 15. Okay, how do we start problems like this? Well, it is generally a pretty good strategy that when we go through and we're trying to figure out what do we want our variable to be, let your variable be what the problem's asking you to solve for. That way, whenever you build a function or build an equation and you solve it, you'll now have the solution to the problem that was asked. So, because the problem says, calculate the width of the strip, then my advice to you would be, let your x be the width of the strip. Now, you could write a let statement, let x represent the width of the strip, but because it's a measurement problem, let's just label it on the diagram. So, when I go to cut off something, that's me in my mind trying to draw what looks like uniform. If I'm going to let x represent the width of the strip, then this width right there is x. I'm just going to zoom in a little bit. That's my x. Now, because it's uniform, if that's x, then that also has to be x. So does that. And lastly, so does that. That's what that problem is telling me. Now, you do not need to label all of those x's on there, but feel free if it helps. Okay, the problem tells me that what's left over, that rectangle in the middle, has to have that area. Okay, well, I know to calculate the area of a rectangle, it's length times width. That means I need the length and the width of that blue rectangle. So how can I come up with it? Well, if you take a look at my diagram, I'm hoping that this is going to run pretty clear. Can you look below the 15? If I drew that purple line all the way across, that is 15 centimeters. But then what I did is I cut off an X from that side. I also cut off an X from that side. That's what leaves me with the blue length. So if I'm trying to figure out how long is that blue line, well then it's the 15 all the way across the bottom minus the 2 X's that I took off, one from each side. And that gives me the length of the blue rectangle. Okay, I think if we've got that, we should be pretty good then to know that the width of the blue rectangle has to be all the way up and down. There's my 9, but then take off an X, take off an X, so it has to be 9 minus 2X. And there are my dimensions of my blue. Okay, really, I did all the heavy lifting there. Like, I am done. The question said the area was that, so area is length times width, and we are good. On a translating day, you are done right there. Obviously, if we were going to solve this thing, you would expand all your brackets, you would collect, and you're going to notice you're going to get a squared x term and a single x term. So now we're going to solve that by either factoring or quadratic formula. There we go. Hopefully not too bad. I'm hoping that we now have an idea of what we're talking about when we say, hey, uniform strip, and we know how to get that thing going. Okay, let's jump into one last problem. Okay, problem 7 is our extension from problem 6. So it says from the previous problem, so I'm just going to draw that diagram again, all the way my original piece, 15 by 9. I cut off an X all the way around. That leaves me with 15 minus 2X and 9 minus 2X. Okay, there was the context. That takes care of the from the previous problem. Now, the new context, if the area of the strip to be taken off of the original sheet is equal to the area of the remaining sheet, then calculate the width of the strip. Okay, what I am going to do is I'm going to translate that sentence exactly as I can, and I want you to try to do the same. So I want you to take, if the area of the strip to be taken off of the original sheet is equal to the area of the remaining sheet, I want you to try to translate that into algebra. And I want you to try it on your own. Okay, give it a shot. Pause the video now. Okay, we're back. So I'm going to do exactly what that says. If the area of the strip to be taken off, that's that blue, really ugly looking brace bracket. The area of the strip, that would be this shaded in blue area. Notice, that's the area of the strip. Well, how could I come up with that blue area? Well, that could be the whole purple rectangle. Like, I want you to imagine that that purple rectangle is shaded in everywhere. And then what I'm going to do is I'm going to now subtract out the red. Like, I'm going to pull that hole being a rectangle, out. When I do that, it leaves me with just the blue shaded in part. So if I took my 15 times 9, that's the whole thing shaded in, subtract out the area of the middle. 15 minus 2x times 9 minus 2x. That would leave me with what I have in the blue. There's my shaded in blue part. Okay, it says that that is equal to, so I'm going to put my equals, and that is equal to the area of the remaining sheet. Well, the area of the remaining sheet is 15 minus 2x times 9 minus 2x. And there we go. We're good. There is a direct translation of that statement. For you to work your way through, we would be expanding the brackets, collecting like terms, and now we're using factoring or formula to be able to solve. Okay, I want to tackle this one a different way because there is something in that relationship that could have allowed us to shortcut that a little bit. Okay, how could we have done it? Remember, this is an alternate way to set up the problem, the equation, I should say. I want you to look at your diagram, and I'm going to zoom in on the diagram. I'm going to use some ratios. The problem said that the area of that blue shaded in part, like I'm really going to shade it in for you. The shaded in part, the strip that's being taken off, is equal to the area that remains. So the blue equals the red. So what that means is that this blue is worth 1 part to this red, which is worth 1 part. They both have the same ratio, 1 to 1. They're equal. But they come together to each represent half of the total. So my blue shaded in portion is half the total, or my red shaded in portion is half the total. So if that's the case, I could create an easier equation to work with. Okay, I'm just going to get rid of a lot of that shaded in part again, and I'm going to shrink that down. Because an equation we could have come up with then is, well, my red rectangle is 15 minus 2x times 9 minus 2x. That's my area. That has to be half of the total. And that could be an easier equation for you to work with. I might argue at least less risk for mistake. Okay, there is an easier way to tackle that problem. There we go. The first equation, direct translation. Second one, that kind of helps me with some ratios a little bit. Okay, I have to be honest with you, I like using ratios. I think it avoids some risk for mistake, but I think it's easier to build your equations with them. So let me change this problem relatively quickly so we can see how those ratios really work. Okay, I want us to acknowledge that is your solution for problem 7. Either the first or the second. You got one of the stars. Okay, I'm going to go through and I'm going to just draw a really rough example of our diagram down below. I don't even care about the labels. I don't care about the X. I don't care about anything. There it is in the bottom. Now I want you to look back up at the question I gave you because I'm going to change the question. I'm going to say, what if the area of the strip to be taken off is, and here's where it's going to get a little ugly, I'm not going to say it's equal to. I'm going to say it's double. Okay, I am changing the problem on you. How can we deal with that? Well, this is kind of a combination of the problems we talked about today. This is going to lead us back to maybe the investment question, the 6 and 4%. But I want to work our way through using ratios. That says the area of the strip to be taken off is double the remaining amount. So if I shaded my diagram the same way I did before, there is my blue. I'm trying to make it as dark as I can make it. That's why I don't want to highlight it. Like, I legit want to make it really dark. There's my strip, the area of my strip, as fast and crudely as I can do it. What I have on the inside is now my rectangle. And same thing, I'm just going to go as quick as I can. I don't need you to be sitting there watching me color. Okay. If I take the new problem that we have up above, and I say that the rectangle on the inside is worth 1 part, then since the area of the strip to be taken off is said to be double, the blue would have to be worth 2 parts. Now, if my language of parts is confusing to you, I want you to imagine this. Imagine there's your diagram, and I told you that the area of the red rectangle was, let's add a 0, 10. Say it was 10 centimeters squared. Well, then if the blue strip's area is double it, it would have to be 20. But notice that that ratio is always in the ratio 1 to 2. If I went backwards and I said, okay, let me get rid of that ratio. Well, what if my red ratio was in, I don't know, let's say that its actual was 11. Let's pick 11. Well, then the blue strips area would have to be double that. And if I look then at that ratio, notice divide both of those by 11, I'm back to 1 to 2. So the ratio of those parts will always relate to each other that way. So what does that mean? Well, it means that for my red section would have 1 part out of a total of 3. Notice the 1 part in the red plus the 2 parts in the blue make the total of the purple rectangle, the original, worth 3. That also tells me that my blue strip has to be 2 parts out of the total of 3. That I could use ratios to build quicker equations. So I'm going to build an equation for both of those. Let's say I looked at it, for the easiest one. If I look at that original equation, the question, if the area of the strip is to be taken off is now double the area of the remaining sheet, then I know that the red, the part that I have on the inside, that part I can calculate my area for really fast. 15 minus 2x times 9 minus 2x, length times width. Well, it's equal to 1/3 of the total. And I could build that equation and be good. Be good. Now I could multiply my 1/3, simplify the right side to one number, expand my brackets on the left, and I'm off to the races. If I don't use ratios, then my equation becomes really complex. Okay, I'm going to try to fit all this on our screen. Here comes the big ugly one. Here comes the direct translation. The area of the strip, 15 times 9, minus the inside, is double the area of the remaining. Well, look at that blue equation. Look at all the brackets you have to expand. Also make a note, you're going to have to subtract all of that stuff on the left. So you better make sure that you subtract or change all of your signs. We have so many spots where we could make mistakes in the blue equation. I am hoping that I have motivated you to use ratios to build these red equations instead. Okay, I think we are good for today. I have thrown a number of problems at you. All the problems that I would make an argument fall into the category of you kind of have to know how to get them started. Okay, your job. Jump in and get as much practice as you can so you don't feel like you have to memorize the starting point. Like you already know it. And then when we get to the point where we're actually solving all of these problems, you should be good. Okay, jump in and get your practice. Best of luck.